Welcome back, everyone. Today we're taking a deep dive into a fascinating chemistry topic that's sure to impress at your next cocktail party.
Oh, this sounds fun.
We're going to be talking about passivation, the
Passivation.
art of self-protecting metals.
Okay, I have to admit that sounds a little intimidating.
I know, right? But trust me, it's surprisingly relatable. Have you ever wondered, why some metals just don't rust?
Yeah, like my stainless steel sink. It's always wet but never rubbity.
Exactly. That's passivation at work.
So what is passivation exactly?
Well, maybe our expert can explain it better.
Sure. Passivation is a natural process where certain metals form this really thin protective layer.
Kind of like an invisible shield.
Yeah, exactly. It's an oxide layer, and it stops the metal from corroding.
So it's like the metal devises its own armor.
You got it. And it's incredibly effective.
So going back to the stainless steel, what's protecting that?
Stainless steel has a passivated chromium oxide layer. That's what gives it that durability.
Is it a thick layer?
Actually, no, it's super thin, like nanometers thick.
Wow, that's amazing. So how does it work? I mean, on a microscopic level.
Well, picture the surface of a metal, right? It's all these atoms ready to react.
Okay.
And when some metals are exposed to oxygen, the atoms on the surface bond with the oxygen atoms.
Like a chemical handshake.
Yeah, exactly. And this creates the metal oxide layer.
And that stops further reactions.
That's right. It acts as a barrier and prevents more oxygen or other corrosive stuff from reaching the metal.
So it's like the oxide layer saying, nope, we're good here, no more reactions.
Exactly. And that's what makes passivated metals so durable.
So passivation is a natural thing, but can engineers use it to make, even better materials?
Oh, absolutely. Engineers have been studying this for ages.
So they're basically copying nature.
Kinda, yeah. It's called biomimicry. They make artificial coatings that mimic this natural protective layer.
So, engineers are copying nature's homework. That's pretty clever.
It is, and it's led to some amazing advances in material science. We can make things stronger, lighter, and way more durable.
Wow. So where do we see these super passivated materials being used?
Think about aerospace components, jet engines, for example.
Yeah, they get super hot, right?
Exactly, and they need to withstand those high temperatures, so engineers use special coatings that create a super passivated layer.
So it's like giving those jet engines an extra layer of armor to handle the heat.
Exactly, and it's not just aerospace. Passivation is used in tons of industries, from construction to electronics.
So this tiny invisible layer is a big deal.
Huge.
Okay, but how can we use this knowledge to impress our friends at a party?
Well, next time someone compliments your stainless steel cookware,
Yeah.
you can casually mention how a thin, invisible layer of chromium oxide is keeping it so shiny.
Ha! That's a great idea. You've turned kitchenware into a science lesson. It's not just about knowing facts. It's about understanding the amazing stuff happening all around us.
Totally. It's about appreciating the world at a microscopic level.
Well said. Now, before we move on to more examples of passivation, what's the most surprising thing you've learned so far? Welcome back to our deep dive. We've learned about how cool this protective layer is, but there's always more to discover, right?
Right.
So what other examples of passivation can we look at?
Well, have you ever thought about aluminum?
Aluminum.
Yeah, it's actually a very reactive metal.
Really? But aluminum foil doesn't rust, does it?
Nope. And guess why?
Passivation.
You got it. Aluminum forms a thin oxide layer on its surface when exposed to air, and that aluminum oxide is really stable. It stops corrosion.
So it's like aluminum is born with its own shield.
Exactly, and that's a big reason why it's used so much, for airplanes, cans, all sorts of stuff.
That reminds me of titanium, too. It's used in medical implants and stuff, right?
Yeah, titanium is amazing. It's biocompatible.
Wait, biocompatible? What does that even mean?
Oh, sorry. It means it gets along well with the human body. It doesn't cause problems when it's implanted.
Ah, okay.
And that's because of its passivated titanium dioxide layer. It protects it from corroding, but it also makes it less likely to, trigger the immune system.
So passivation isn't just about keeping things from falling apart. It's also about making sure implants are safe.
Exactly. It's amazing how nature does that. But, engineers are trying to make it even better.
Right, with those super passivation coatings, where are they used besides aerospace and medical stuff, like real-world examples?
Okay, well, think about spacecraft heat shields.
Oh yeah, those things get crazy hot, right?
Super hot. They need to withstand insane temperatures during re-entry.
It's like diving into fire.
Pretty much. And to survive that, engineers use those special coatings. They make a super passivated layer on the surface.
So it's like a heat-resistant shield for the spacecraft.
Exactly. And it's not just for extreme heat either. They're also used to protect electronics from moisture and things like that.
Wow, so my laptop is using the same science that protects spacecraft from burning up. That's pretty cool.
It is. Passivation is everywhere.
It's like the microscopic world has its own set of rules, And if we understand that, we can do some amazing things. But I have to ask, are there, like, any downsides to this?
Well, no technology is perfect, right?
Right.
Passivation is really good at stopping corrosion, but the layer can get damaged. Scratches, chemicals, stuff like that.
So it's not completely invincible.
Not quite, but, scientists are always working on making it better. They're looking for ways to make the passivation layer self-healing.
Wait, hold on. Self-healing metals, is that even real? It sounds like science fiction.
I know, right? But it's an actual area of research. Imagine a bridge that could, fix its own cracks.
That would be incredible. How would that even work?
Well, one way to trying is to embed tiny capsules of a healing agent in the metal. So when there's a crack, the capsules break open, and then the healing agent reacts and seals the crack.
That's like the metal has its own little first aid kit.
Yeah, exactly. They're trying other things, too, all based on manipulating materials at the microscopic level. It's still a new area of research, but it has huge potential.
This is amazing. We've gone from talking about invisible shields to self-healing metals.
I know. It's mind-blowing what's happening at the nanoscale.
It really is. Okay, so we've talked about the power of passivation and the possibilities of these self-healing metals. But where is all this going? What about the future of this technology?
Well, that's a great question.
Welcome back to the Deep Dive. We've been on quite a journey with passivation, haven't we? From those natural shields to the crazy idea of self-healing metals.
It's been a wild ride.
It has. But where do we go from here? What's next for this technology?
Well, one area that has a lot of potential is smart materials.
Smart materials. Okay, you're going to have to explain that one. What makes a material smart?
Well, imagine materials that can actually sense changes in their environment and then respond to them.
Okay, I'm listening.
Like a bridge that can detect a tiny crack forming and then release a healing agent to fix it.
So it's like the bridge is taking care of itself.
Exactly. And smart materials can do more than just heal. Some can change color, shape, or even how well they conduct electricity depending on the temperature, light, or pressure.
Hold on, are you saying we could have clothes that change color with our mood or buildings that adjust their temperature based on the weather? That's straight out of a sci-fi movie.
I know, right? But it's becoming a reality or already developing materials like that.
Like what?
Shape memory alloys, you can bend them out of shape, and then when you heat them up, they go back to their original form.
Wow, that's incredible. So if we combine these smart materials with what we know about passivation, are we talking about a whole new era for materials?
Oh, absolutely. This could change everything. Healthcare, construction, transportation, energy. Think about lighter, stronger airplanes, self-cleaning solar panels, medical implants that can adapt to the body.
It's pretty exciting to think about all the possibilities, but with all this progress, are there any downsides? Like ethical concerns or something?
That's a good point. We always have to think about the implications of new technology.
Yeah.
With material science, we need to think about the environmental impact of making these new materials, and what might happen if self-healing or smart materials end up in the environment accidentally. And of course, we have to think about who has access to this technology and whether it's affordable.
So while there's a lot of potential, we need to be cautious and make sure we're using this technology responsibly.
Exactly. We need to talk about the ethical and social impacts of new technology, and we need to be open to different perspectives.
Well said. It's something we all need to be aware of as technology keeps advancing.
Absolutely.
Well, I think we've given everyone a lot to think about today, from invisible fields to self-healing metals and even smart materials. The world of material science is full of surprises.
It really is.
So, next time you're at a party, don't be afraid to share some of this knowledge. You might even inspire someone to explore the world of materials, science themselves. Thanks for joining us on this deep dive into passivation. And until next time, keep exploring, keep learning, and never stop questioning the world around you.